Inside silicon, the technology behind everything. Powered by Semiconductor.
You know, for over half a century, the entire digital revolution has been running on one simple, powerful idea: make the transistors smaller. We went from transistors the size of a human hair down to nanometers, and now we're literally talking about the scale of just a handful of atoms. This incredible shrinking act has been the engine of all progress, but it's also leading us to a huge question that's keeping some of the smartest people in the world up at night.
I mean, really, what happens when we smack right into the fundamental wall of physics? Is that it? Is silicon scaling over? And if it is, what does that mean for, well, everything? For our phones, for AI, for the future of computing. This is, without a doubt, the central challenge facing the entire semiconductor industry right now.
So let's dive into why this is such a massive problem. See, we're not just fighting against tricky engineering challenges anymore. No, we've stumbled into a whole new battleground, and this time our opponent is physics itself.
Think about it. Every single leap forward in tech that you've seen in your lifetime, every mind-blowing AI model, every ridiculously powerful GPU, every sleek new smartphone, it's all been powered by this one simple mantra: more performance, less power, cramming more and more computing into every single square millimeter of silicon. This isn't some academic exercise. This is about the very engine that powers our modern world.
Okay, so to really get a grip on the problem, we've got to clear up a pretty common misconception. When you hear that some company is releasing a new 2-nanometer chip, what does that number actually mean? Well, the answer might surprise you.
Yeah, for a long time now, that node name, it hasn't been a literal measurement of anything on the chip. It's basically a marketing term. It's a label for a new generation of technology that tells you, hey, this is a big step up in transistor density and performance. The critical thing to remember is that we have to look past the label and down at the actual physics.
And this is where it gets really weird and interesting. For decades, chip designers could pretend that electrons were like little tiny marbles flowing through a pipe. You know, nice, predictable, classical physics. But down at the 2-nanometer scale, that whole assumption just completely falls apart. Electrons stop acting like particles and start behaving like waves of probability, governed by the totally bizarre rules of quantum mechanics.
Just let this number sink in for a second. The gate of a transistor, the tiny switch that controls everything, is only about 10 to 12 atomic layers thick. At that scale, a single atom being in the wrong place can completely change how the device works. We are literally building machines at the very edge of physical reality.
So if we're running out of room to shrink things side to side, horizontally, what's the solution? Well, the industry's answer is both simple and, frankly, brilliant. We go vertical. If you can't build out, you just have to build up. And what's so cool about this is that we've actually been on this 3D path for a while now. We said goodbye to the old flat 2D planar transistors years ago. Then we moved to FinFETs, which was like lifting the channel up and wrapping the gate around 3 sides of it. The next step was nanosheets, or gate-all-around, which completely surrounds the channel for even better control. And the next logical step, as you can see, is the CFET, where we literally start stacking different types of transistors right on top of each other.
This quote just nails it. It perfectly captures the massive paradigm shift that's happening. The future of scaling isn't just about making the transistor's footprint smaller anymore. It's about designing these clever new 3D architectures that let us pack more computing power into the exact same area by building skyward.
So is stacking transistors vertically the only answer? Not a chance. The industry is way too smart to bet everything on a single horse. Instead, what's happening is we're pursuing 3 major strategies all at the same time, in parallel, to see what's really going to carry us into the next decade.
Okay, so path number 1, as we've been talking about, is vertical scaling with these things called complementary FETs, or CFETs. By stacking the N-type and P-type transistors, which are the basic building blocks of all digital logic, you can effectively double your density without making the chip's floor plan any bigger. It's a huge potential win, but believe me, it comes with enormous challenges in manufacturing and just figuring out how to get all the heat out.
Path number 2 is a bit more radical. It asks, what if we move beyond silicon itself? Researchers at major labs like IMAC are exploring brand new materials for the transistor channel, things like germanium or even these wild 2D materials like molybdenum disulfide. The dream is that these materials will let electrons flow with way less resistance, giving us faster switches at lower, more efficient voltages. But actually integrating them into today's massive silicon factories, that is a monumental task.
And the third path is all about zooming out. If it's getting crazy expensive and difficult to scale one single giant chip, why not just break it into smaller pieces? This is the whole idea behind chiplets and advanced packaging. You build smaller, specialized chips, or chiplets, and then you stitch them all together in a complex 3D stack. Here, the innovation shifts away from the individual transistor and focuses on how you cleverly integrate the entire system.
So what does all of this mean for the engineers who are actually designing these chips every day? How do all these new physical limits actually change their job? Well, it turns out they change pretty much everything.
I mean, just look at this list. These are not abstract concepts from a textbook anymore. These are real first-order design problems. Quantum tunneling means your electrons are literally leaking through walls they're not supposed to. Random dopant fluctuations mean that two transistors you designed to be identical can behave totally differently just because of a few stray atoms. Suddenly, physics isn't a homework problem. It's a yield problem that can kill your whole project.
And this table just lays out the shift in thinking perfectly. In the old days, the focus was all on logic and just getting the clock speed as high as possible. But now, in this physics-aware world, look at the focus. It's all about power, thermals, and that variability we were just talking about. The big challenge isn't just raw speed anymore. It's about managing the fundamental physics to create a chip that's reliable and won't, melt. With all these fundamental changes happening, what does this mean for the people who are actually going to build this future? What skills do the engineers of tomorrow really need to focus on to be a part of this new era?
The focus is shifting, big time. It's not enough anymore to just know how to write code that turns into logic gates. The most valuable engineers moving forward are going to be the ones with a deep, gut-level understanding of device physics, who get the manufacturing constraints, and who can think across all the different domains, from the atomic level of the silicon process all the way up to the entire system architecture.
And here's the economic reality check. These bleeding-edge nodes are becoming unbelievably expensive to develop, so they're not going to be used for every little thing. They'll be reserved for the most demanding applications out there: massive AI accelerators, high-performance supercomputers, and other strategic technologies. The future isn't just about smaller transistors, it's about smarter integration. So is Moore's Law dead? I absolutely love this quote because it reframes the entire conversation. It's not dying, it's mutating. It's evolving from a simple 2D shrinking exercise into this incredibly complex, multifaceted challenge that involves new materials, wild 3D architectures, and brilliant system-level integration.
The most important thing to take away from all this is that this isn't an ending. It's a transformation. The simple, straight road is over, but in its place is a future that's going to require more creativity, more cross-disciplinary knowledge, and more raw innovation than ever before. The question isn't if we can continue to scale anymore, it's how. So the real question, the one I want to leave you with, is this: what part will you play in building what comes next?
Inside Silicon, the technology behind everything. Powered by Semiconductor.